Okay, so we're going to be talking about Pascal's principle. And Pascal's principle is the key. This is 1F, for those of you keeping track. So 1F, Pascal's principle is the principle behind equal pressures, equal force transmission, in a fluid. And so that part is what explains why fluids are not compressible. And then the other thing Pascal's principle tells us, there's a couple more. The second one is, why does pressure increase as you go deeper into a fluid? So it's also going to answer that question. So it's due to extra weight above you. And then the third thing that it handles for us is hydraulics. It explains why hydraulics work. Man, if I could spell today. Hydraulic lifts, jacks, etc. work. So let's start with the first one. The first one is this, and I want you, if you can, take the time to pause this video and answer this question in your head before I do this. And I'm going to try to set up some videos where you can see what we're doing in class so that you can see us actually do these. So let's imagine that we have a lovely little container filled with fluid, nice water container, and I drop a small button. Let's not do a button, let's do a small rubber stopper. So I'm going to take a small rubber stopper and I'm going to put it in the water. Okay? So if we do that, my question to you is, let's imagine if we put this whole thing on a balance beam with a readout that told us how much mass is on our scale. So let's imagine to start with that the mass of the water and the container, so the mass of the container with the water is 200 grams. Okay, just a small cup, kind of like a bathroom size cup, you know. And so we put that on the container. My question to you is, if we then have the rubber stopper floating, partially submerged into our fluid, here's my question. Does the scale reading change when the rubber stopper is inside? Is in the water. And if you want to pause and think about that, chew on it for a second, I'm going to let you do that. Obviously, I will keep talking because you can hit pause on the video. You don't need me to actually stop talking to answer the question. So, the answer to the question is, the mass will increase by the same amount as the mass of the stopper. And here's why. If I put the stopper into my water, there is now more mass altogether sitting on the bottom of the container where the mass is being read. So the fact that it floats, there's still mass there. There's still an object there, and it's floating. If I was to take a rock and a rock would sink, if I put the same mass rock as the rubber stopper, the rock will sink, but we'll still get the exact same mass change at the bottom of this container. So that one's pretty easy. Now here's my next question. What about this? Does the force, and therefore the pressure, and pressure, actually do the force and pressure change when the stopper is added? When the stopper is added. Okay, so I've now applied a force downward onto the top of the water. If I apply a force downward on top of the water, once again, please feel free to stop and think about this. Maybe look at a video, maybe read your notes, maybe read the book. But I'm going to give you the answer here in just a second. But if you want to stop, here's your chance to stop. Okay, so the force, if I was to now measure the force at the bottom of this container, say I measure the force right there. When I have put the stopper in, there is a new force down on the water. And you say, how do you get a force on the water? You can't push water. Well, you can kind of push water because it creates a solid object. We're treating it like it's a continuous object. So you can think of it like if I had Jell-O, I could mash down on the Jell-O, and the mashing down on the Jell-O would transmit all the way through the Jell-O. If I push hard enough, my finger will penetrate it, so the normal force will get broken. But if I push down on the water, I can mash down on the water, but the water doesn't squish, but it does transfer the force to the bottom of the scale reading. And so the force now at the bottom will be larger than it was before. So let me ask you this. Let's take this container one more time, and I'm going to make it a little bit bigger. And here's what I'm going to ask you now. Here's my rubber stopper doing its thing, sitting on top up there. And I want to put a pressure measure here, one that's directly, so this is to the right, this will be to the left, and this one will be directly below the stopper. If I measure the force in each of those three places, is the force the same? Is the force different? Is the force different on A and C? A and C are the same, but B is different because it's under the stopper, or not? Well, Pascal's principle here is going to tell us that that force got transmitted everywhere. Okay? So the force that the weight, if you will, of the stopper applies to the water gets transmitted in all different directions. Okay? And these these dots or these pressure measures are all at the bottom of the liquid. So all of these columns, even though the column over C does not contain the stopper, the column over B does. And the column over B, if you think about it, if there was a net force in some direction, the net force would cause the water molecules to move around. So water molecules can't have a higher pressure at B than at C. B must be equal to C, because otherwise the fluid on the bottom would move. They would move from high pressure to low pressure. And what would we see? Well, if the pressure really is higher under the stopper, if this column really has the most pressure, that would mean the water would start to fill up these directions, and so the water level on the sides would be bumped up, and the water level in the middle, the stopper would start to sink down. And I've never seen water do that in my life. The sides don't raise up so that they're like two little twin peaks, and the stopper goes down until the forces are balanced. So the column doesn't really matter about what the column shape is above you. It does, however, matter what the area below is. The bottom surface area is going to make a difference because we're taking the force total, weight of stopper and weight of fluid, and it's being carried across the whole bottom of the container. And so we know that Pascal's principle is going to make the volume of water, not the volume of water, the pressure of the water at those three places the same, and if the pressure is the same, then the force will also have to be the same. Okay, so let's look at a use of hydraulics. What does hydraulics do? And so this first example hits the equal force transmission, and why do you increase in, I haven't got to the why do you increase, so let's do the why does the pressure increase as you go down. Well, most of you know that if you've ever looked at a water tower, the bands at the bottom are bigger than the bands at the top. But if you can imagine for a second Hoover Dam with me, Hoover Dam is very thin at the top, and at the base, here's the front, at the base it is very, very wide. So you can't see that directly because of course the water's back there, but the base of Hoover Dam, the front facing would be over here, and as you go down, these cross-sectional areas that you look at, they get much wider than you have at the top. So at the top, there's a nice little walkway up here where people can walk and you can look down on both sides. But as you go down, the depth, the thickness of the wall increases. And you may wonder, why is that necessary? Well, it's necessary for what we were just talking about. If we have, let's say we have a pool of water here, at various depths in the fluid, say here's A, here's B, and here's C. At A, it only has to deal with this water level all the way across A. If you can kind of think of it as a thin, tiny thin sheet of paper, it has the weight of the water above it, which would be all of this amount, and the weight of the atmosphere. So there's our atmosphere. All the air in the atmosphere is sitting down, so the weight of the air is pushing down, and weight of water is pushing down. So if we were able to slice the water into a thin sheet at that particular level, at some particular height, the force down would be the summation of these two weights. And so since you're on that level, once again, the particles are not moving up and down in the fluid. We are treating this as if it's continuous. So we are literally treating the water as if there's a thin sheet of water, and all the particles in that thin sheet don't go up, they don't go down, they can't move left or right. They're just all kind of vibrating at that same height. But what happens if we go down to the sheet at B? What has happened now to our weight of water? Well, our weight of water has doubled, if you will. So we have twice as much water weight. And so the pressure, because pressure is force per area, the pressure is going to be larger in this location than it was at point A. All of the places on B, any other place you pick on that thin sheet, will have the exact same pressure and experience the exact same force. But they will experience a different force than at point A. And then last but not least, at point C, in this picture, you would have the most force and most pressure because you are the deepest in the fluid, because you have most depth. So this is why we must do things when people scuba dive, or when they go down in a sub, or when they're doing explorations in the little submersibles. They have to do something to help prevent the compression of their lungs due to air. So we pressurize the tanks. They breathe pressurized air inside the submarines and inside the submersibles. They change the pressure on the inside so that the pressure on the inside and the pressure on the outside are similar. We keep the pressure on the inside pretty close to what the ground level is inside a sub, and we allow the metal sheathing, the surface of the sub, or the metal coating of the sub, or the skin of the sub, to help us deal with the pressure changes. So, if you go deeper in a fluid, you're going to have more pressure. That's one of the things Pascal said. And it doesn't matter. If I put a boat over here on the water, here's my cute little boat, the pressure on everybody goes up. A's pressure is increased, B's pressure is increased, and C's pressure is increased, because that force that is now applied to that continuous blob of water, that continuous mass of water, experiences all the forces anywhere within it. We transfer it from one to the other. Okay, so now let's look at the last one, the hydraulics, and I'm going to work a couple of problems. Actually, I'm going to do problem solving on a separate page, but I'm going to give you the idea of what's happening in hydraulics. So hydraulics says that, let's go with, you have something like this. A hydraulic system would look something like this, where you have a small piston and you have a large piston. And just to give you an idea, maybe this is where your brake pedal is, so that when you push down on your brake pedal, we have brake fluid within this line. And this is where your brake pad is on your car. So you push on the brake pedal and you can't compress the fluid. So if I push down here, that force, as Pascal said, gets transmitted over here. So how does that help us? I mean, because if I stick my feet outside a car, I'm not going to stick my foot out on the side of the road and be able to stop the car just by pushing down with my foot. And yet I can do that with the brake pedal. It comes from the fact, pardon me, that pressure is a ratio. So pressure is the ratio of force to area. And so let's keep this simple once again. Keep it simple, smarty pants. Self-talk is positive, not keep it simple, stupid, but keep it simple, smarty pants, so that we can get this done. So if the pressure is this number, then we can use that. It's going to be the same on the other side. So let's say that the force here is 40 newtons and the area is 10 square centimeters. Okay, so our force would be 40 newtons over 10 square centimeters, and that would be equal to 4 newtons per centimeter squared. Now here's the cool part. On the other side, I have any other ratio that I want to use as long as it reduces to 4. So let's imagine over here that we had 100 square centimeters. Then the numerator would become 400 newtons. So now my 40 newtons has been turned into 400 newtons through the magic of ratios, or through the magic of proportions. And so what we do with our brake pedal is, if you've ever looked at the little line that comes out of the brake pedal, it's a tiny, tiny little diameter tube. And the one on the brake pads is much larger. And so we're getting much, much, much more force coming out. But the tricky bit is this. This side of the brake pedal side, the piston will actually move. I'm not going to draw that again. The piston will move way down here, so that now it's taken care of in this same space, but it's now pushed way down into the fluid, where the side of the brake pad, it's probably only gone up just a little tiny bit from where it was initially. So you have not, give us our brake pad there, our brake pad on this side, here's where it was to start with, it's only moved this tiny little amount, where the brake pedal has moved a large amount. So we also, with hydraulics, and this is what I was going to say when I started writing and then I didn't finish it, hydraulics trade force for distance. If I want to output a huge force, that's great. but that means I have to apply the little force over a much larger area. And so all the hydraulic problems will be worked as the pressures are the same, they're transmitted evenly, and yes, I'm adding pressure to the mix when I push on the brake pedal. So now there's a new amount of pressure, but it's the same amount of pressure for everybody, everywhere. You've added the same amount. And so here we go. So next time I will get to you and we'll talk about the how to do the math parts here. But the math is pretty straightforward as far as how do you find different things, and that's where we'll pick up next time.